Good evening. I told you I'd make some videos, so let's go ahead and let's take some looks at modeling functions. So we're going to use the first derivative to model the behavior of f of x. Now f of x is a polynomial, and therefore its domain is all reals. Okay? So we start by looking at its derivative. And the derivative of the sum or difference is the sum or difference of the derivatives, and I end up with a polynomial that is 1 degree less, and I don't believe I made any mistakes. Now when I look at that, the greatest common factor is 5x squared, so I'm going to go ahead and factor that out. So that's x squared minus 4x plus 3. That is 5x squared. This is x minus 1 times x minus 3. Now, f prime is itself a fourth degree polynomial, and therefore it exists for all reals. So that's the first part of the definition of critical point for f of x. And now the second part is, when is this 0? Well, this is 0 if 5x squared is 0, or x minus 1 is 0, or x minus 3 is 0. Now I would hope that you could do these by inspection. Now I'm going to build a number line, and I'm going to do this a little bit differently than before. 5x squared is a parabola. Its 0 is 0, but it's positive everywhere else. Then I'm going to go back to algebra 1, and I'm going to look at the parabola y equals the product of x minus 1 times x minus 3. That parabola opens upwards. That means that the vertex is between 1 and 3, underneath the axes, and then outside of those zeros it's positive. Okay. Now f prime of x. Now I just want to do a couple different things here. I mark it. Now be careful here, okay? Because 0, 1, and 3 are critical values of f of x. Why? Because f prime of x is 0 there in each case. But it's not critical values. It's not a 0 for each of these parts of the sign chart, the number lines building. Now I'm just going to go back to algebra 1 and say the product of two positives, I hope, is still positive. The product, oops, sorry about that, I slipped there and didn't see it. So here's a stationary point. The product of a positive and negative is negative, and the product of two positives. Okay, so if you think about it, this is a stationary point. This is a local max. This is a local min. Okay. F is increasing on. You look at your sign chart. Where is my derivative positive? Now, a lot of students are saying, Mr. Isaac, it's increasing at 0. It is, but not using the theorem you're using. The theorem you're using says a function is increasing at a point if and only if its derivative at that value is positive. 0 is neither positive nor is it negative. So there's explaining where it's increasing, because f prime, and this time I'll just say is positive on the interval. And I just get the intervals and I copy them down. They don't want you to say the intervals. Yeah, I know what you're talking about, but don't do it. F is decreasing on the interval from 1 to 3. Why? Because now, since I talked about positive there, I'm just going to be consistent, is negative on the interval from the open interval from 1 to 3. Now I go back to the sign chart and, okay, at x equals 1, f of x attains a local maximum. Now, the theorem says it's a critical point there, so I look right here. Oh, look, it's a critical point there. F prime of 1 is 0. And f prime changes signs from positive to negative. Now, don't stop at x equals 1. Okay? Now, I'm running out of room, so I'm just going to say the sentence. This is a local minimum. On the next example, I'll use relative min max, but this time I'll use local min. At x equals 3, f of x attains a local minimum. Why? Because, oops, I forgot the word because. Because f prime of 3 is 0, and f prime changes signs from negative to positive at x equals 3. So as you can see, we're consistent. I hope this example helped. Ooh, that would have been a mess.